Okay, then we will move forward. And this is in continuation with the yesterday's talk about the single source shortest path in case of the negative edged or negative weighted graphs, which was a kind of disadvantage for the Dijkstra's algorithm. And to solve such issues, the Bellman-Ford algorithm proposed by this man, which is even working in case of a negative cost or a negative weight. So what he says is that if there is a negative edge in a graph, so at most v minus 1 number of times we have to relax every node of that graph. A relaxation we saw yesterday, what we also called as updation. So this Bellman-Ford says that if there is a negative edge in a graph, so relax every node maximum number of times v minus 1 times. So if there are 4 nodes, so iterate this loop 3 times and relax each and every node for at most 3 times, depending upon the number of nodes. And whatever the results you get after relaxing for v minus 1 times, the final result you get will be the minimum cost distance of those nodes from the source node. So if in the present graph, which consists of 4 nodes, A, B, C, and D. So A will be taken as the starting node, and if we see there are 2 nodes connected to this A, which are B and C. The cost of the node A is here 0 because it is the self node. There is no distance in between A and A. And what Bellman-Ford also says that in place of Dijkstra's algorithm, he says that first iteration, every node has to be kept cost of infinity. Like yesterday in Dijkstra's algorithm, we saw that the distance between the 2 nodes was to be taken as the cost of that node. So the only difference here is that in the first case, that is the first iteration, every node has to be initialized with a cost of infinity. Infinity, infinity, infinity. So this will become a kind of one iteration. We will maintain a count here and we see for how many times we have relaxed this graph. So when we initialize all the connected nodes to infinity, this becomes the first iteration. Count will become equal to 1. So as to see whether we have reached to this condition, which is being given by this Bellman-Ford. So now in the next iteration, we see that this B node is connected to A with a distance of 1 in between them. So again, we will use that relaxation formula which we saw yesterday, that the distance between the 2 nodes, is it less than the cost of this one, is 1 less than infinity. Okay, the condition is true, so we will update the cost of this node. So infinity will be erased or crossed and it will be updated to 1. Similarly, the C node is also connected to A. Again, the distance between is 2. So is d of u comma v plus d of u less than d of v? Yes, it is less than because the distance from A to C is 2 and here it was infinity. So when it is less than, we will again update the cost of this node to 2. Okay. So now this will become the second iteration and we see in the third one, This node is covered. Now it is the turn of these two nodes. If we take the node B as an example, it is not connected to any other node, so it will be kept as such. But if we now take node C is connected to this node D. What is D? And initially, the cost of this vertex was infinity. And when we update it, relax it, it is 2 plus 3, this distance, that will become 5. Again, it is less than infinity, so it will be updated. All right. Now we see that this node is done, this node is done, this node is done. Now we go to this one, this node, and we see what are the connected vertices to this node D. And here it is node B. And since if we calculate the distance of node B via this path, this will be cost 5 plus this minus 6. That will be equal to minus 1. And this one, which was already the cost of this node B via this A, that will be again updated to minus 1. So in total, we have made the updation inside the graph V minus 1 number of times. Okay, so we will stop here, and the cost to every node from the starting node, that will be the minimum cost or minimum distance from single source A to all the other nodes using the Bellman-Ford algorithm. Okay, so what it says is that even if there is a negative edge, initially we update all the nodes connected to the source node as infinity. Only one node is being kept as 0, that is the starting node. Then we relax these nodes which are connected to the source node. And relax means we update their cost, which we did yesterday. The formula is again the same. Okay, d of u plus c u of v is equal to d of u v. So for how many times we need to relax those nodes? So this man says we need to relax at most v minus 1 number of times. So if there are 4 nodes, 3 times count. That is why we maintain this variable to find out how many times we have relaxed those nodes. When it is 3 times, number of nodes are 4, we don't need to go further, or we don't need to move forward. According to this person, we should be satisfied that these are the minimum distances from the source node. Okay. So now, if we are having the slight modification to this graph, you see it is just like the same graph. The only difference is that we are adding one more edge in between B and C with a cost of 1. The remaining things are same here. If we add one more edge in between these two vertices B and C, and keeping all the remaining things as such, we will try to solve such graphs using the same logic of Bellman-Ford. So again, we will start with A, keeping its cost as 0, because this is the parent or the source node. And we will update the nodes of all other connected vertices to the source vertices and infinity in the first iteration. Then in the second one, we will try to relax the nodes now. And what will be the nodes which needs to be relaxed are the nodes which are directly connected to this A. And in this iteration, we are having nodes B and C which are connected to the source node A. So using the same relaxation distance, this 1 will be updated to here because it is less than infinity. This 2 will be updated here because it is less than infinity. So distance to B is 1, distance to C is 2. This one is still not reachable. So when we reach to this node, means in the third iteration, we will now see the distance of D from this A. Already it is 2 for C. So this 2 plus 3, it will become 5 for this D. Till now it is same what we did. Okay. And this is 5 minutes, second iteration is completed. Now we reach to this node D. and we try to update its connected nodes, and there is node B which is connected to this node D. All right, so already it is 5 and this is 6, so it will get added up, so this will become -1. So from this path, if we go from source node via this path, we need only -1 cost to reach here, while as from A it was needing 1. So this is greater than, and we will update it with the minimum 1. It will become minus. So according to Bellman, this is where we were supposed to stop, because we have reached maximum V minus 1 number of times, because this is the same thing which we did in the previous graph. But for our sake or for our understanding, let's take one more step. Let's ignore this Bellman-Ford. Let's try to go it V times again. That's 3 plus 1 times. We see when we are here, if we see it's the cost of B is -1. Okay. So if we now go, what are the connected components to B? Connected component is C. Okay. So the connected vertices to B is C. If we now try to relax this vertices again, this cost of B is -1. So the distance from going from B to C is +1 here. -1 plus 1, that will become 0. And the weight of this C was 2 in the previous iteration. So 0 is less than 2. So the vertices C will get updated to 0. Okay. So according to Bellman, 2 was the minimum weight for it when we iterate it V minus 1 times. But when we tried to ignore this man's assumption or whatever he said, we get even lower weight which he proposed. And if we now again take C as the source node, and we see what are the components or nodes connected to this C. Only one node is connected, that is D, and its weight was 5 in the previous step from the Bellman-Ford assumption. Now when its weight got updated to 0, so 0 plus 3, that will become 3. Even this node's weight is wrong from the Bellman-Ford. So this way we see that in such kind of graphs where there is this type of circle or there is this type of closed component inside the graph, okay, if there is a closed component within a graph with negative edge, the Bellman-Ford does not work there. So the problem which was present in the Dijkstra's algorithm, it may or it may not work with negative edges. The Bellman-Ford come up with some new idea, and in which he proposed this algorithm which worked fine when there was no circle or there was no closed path in a graph. But again, this problem is for the Bellman-Ford, that if there is a negative edge but there is a closed path also, so this V minus 1 times proposal given by this man does not hold. So a cycle present inside a negative graph does not work Bellman-Ford for that thing. Okay. But okay, this is the algorithm of the Bellman-Ford. It is just the same thing to initialize all the vertices to infinity, excluding the parent, that is the source one, and to then iterate V minus 1 number of times and relax the nodes by using the previous distance formula. Now this we are studying about the various techniques of greedy approach. And till now we have studied 5 techniques which are following the greedy approach for solving a problem. And the 6th one is the optimal merge pattern. And this merge pattern is used in 2 cases. Its first application is in Huffman coding. Huffman coding is a kind of data compression technique. The merge pattern is having the advantage in Huffman coding. And the second application where we use this merge pattern is in merge sort. And merge sort is itself a divide and conquer approach. That's not a greedy one. So that will be discussed in the third unit once we complete the second unit completely. So before going actually to the Huffman coding, I would like to have a little bit discussion upon this thing. You see, we are having two lists or two arrays given. You can take it any, either list or array. So there is a list by the name of A which contains 4 elements, 3, 8, 12, 20. And there is another list by the name of B which contains again 4 elements, 5, 9, 11, 16. And we need to now merge those two lists, A and B. But the merging should be in sorted order. Already this A is in sorted order. You see 3, 8, 12. This B is also in sorted order. So the thing which we conclude from here is that merging always works when the lists are in sorted order. If these lists A and B would have been in unsorted order, then merging was not possible. So when we use the same merging in the merge sort, the condition will be same. We need to merge these two sorted lists into another third sorted list C. And how we do that is we compare the first element of this list with the first element of this list. And whatever is minimum among them, we store it in third list by the name of C. And the same thing is written here in the form of the codes that we compare the first element or this A I points to 3, J points to 5. We compare both elements. And then we store the minimum in C. If it is A is minimum, so we store C, it in C of K. Or if B is minimum, then we again store it in C of K. And we increment the K by 1 because when we store here 3 and 5 we compare. So 3 is less, we will store it here and K will get incremented to the next location. Same here, I will get incremented to the next location. In the next iteration, we will compare these two, 5 and 8. Since now 5 is less, so we will store 5 here and increment K to the next vacant location, which is this one. Similarly, J will be incremented. That's why we are writing here B J plus plus. So post incrementer operator. Firstly, it will be assigned, then it will be incremented. Now in the next iteration, 8 and 9 will be compared to each other. This way, we will be able to merge all those elements of A and B in a C array in a sorted order. And one more thing which will be present at the end of this merging will be there will be some elements inside A or inside B which will remain individual at the end. Because when we compare this with that, this with that, this with that, this with that diagonally, element either here or one element either here will remain as such. There will be no element in the second list to be compared. So for that element, it means whatever the remaining element is, that will be the maximum. Yes. So we will take that element directly and store it here at C K plus 1 location. Whether it is A of I, the last element, because I will be also incremented to that location. Similarly, if it is the remaining element of J, J will be also incremented to that location. Take that B of J element and store it in C of K and increment K by 1 move. Okay, and this process is known as merging, written here only in those 4 steps. So as I said, this should be sorted, this should be sorted. And when we do the merging, if the number of elements in the list A is equal to M and the number of elements in list N is list B is equal to N. So the total time it will take for us to merge those M and N elements will be m plus n, the number of elements in the first and the number of elements in the second. Okay, so here it is 4 elements here, 4 elements here, so it would mean that it would take 8 units for us to merge, make a single list of those two lists which are sorted. Now we take another example just like the same, and in place of two lists we now take 4 lists, A, B, C and D, and the number of data points or number of files in A is 6, so it is an array of 6 elements like that sorted. B 5 elements, C array of 2 elements, those are also sorted. D is array of 3 elements, again that is sorted. So now I need to again do the merging. Okay, so I will go to this step and I will again write it A, B, C, D. The total number of files contained in A6, B5, C2, 3, D3. So there exist different ways of merging. And when different ways of merging exist or different ways of doing anything exists, we are interested in either the top one or the lower one. And that becomes the greedy approach. So here we will try to find out the total time. Like here it took m plus n. We know now if it is of size m, and similarly in this case it is p, q, r, s, so it will take p plus q plus r like this. So we are interested in finding a merge pattern which will take least amount of time. So if we take this example here and we start merging from the left side, so it means this array contains 6 elements plus this array contains 5 elements, and when we merge them to A and B, we need m plus n, that's 11. Okay, from the previous example. Now when the 11th time unit is needed for merging these two, so these are merged. Now we will merge the another list C with these previously two merged list. So already it was taking 11 for it, so plus it will take this 2 for it, that's 13. Okay, and when we merged this A, B and C, now with this A, B, C, that's 13, we will merge the another sorted list D, which contains 3 data points inside it. So that it will take 13 plus these 3, that is 16. All right. So the total time or the total complexity in this case will be the addition of all the external nodes. That's 11 plus 13 plus 16. All right. So it will take 14 units or 14 time units for us to merge this 4 files or lists if we follow this merge pattern. Now, if we try to make a little change, the everything remains the same. The only change we will do is that we will change the pattern of merging. A, B, C, D is again same, 6, 5, 2, 3 is again same. Initially, we will merge these two files, A and B. 6 plus 5, that's 11. Then we will merge these two, C, D. 2 plus 3, that's 5. Once this is done, we will merge these two. 11 plus 5, that is 16. Okay, so in this case, the total time it will need to do merging will be 11 plus 16 plus 5. That's equal to 32. So we got some clues from here is that if we merge the smallest files initially, the smallest file means C and D. If we merge smallest data points initially, the total time gets decreased. Here we merged 2, 3 and 6, 5. The total time got decreased from this merge pattern. Now we change the merging pattern and we go to this step. Taking the same example, we say let's start from right side, this side, and we will merge the least among those four data points. The least ones are 2 and 3. Let's merge them initially. 2 plus 3 will get equal to 5. Then the next least and the list, that is this 5. Let's merge it with this. 5 plus 5, that will become 10. Then the next least in the list is this 6. 6 plus 10, it will become 16. So in the present case, if we calculate the total time, it will take is 16 plus 10 plus 5. That is equal to 31. So we have been able to find a greedy method for merging which is optimal in nature. So what does it mean that two smaller lists, or we can say the pair among those lists which is smaller in nature. Here 2, 3 becomes one pair which is the least among all those, merge that initially. Then the next minimum which is 5. This 5 and this 5 will become another pair in the next iteration, smallest one, merge that. Then 10 and the only one remaining is 6, merge that. If we follow such greedy approach, we are guaranteed to get the minimum cost every time. And this is the logic being applied by the Huffman. The Huffman uses this logic which I am saying for doing the data compression later on. And that is also part of the lecture. So here an example is given to throw more light on the previous example. Now in place of 4, we are having 5 lists x1 to x5 with the sizes given as 20, 30, 10, 5, 30. Okay. So the first thing is always that when the list is not given in the order, means neither it is in ascending order nor it is in descending. We need to perform this step ourselves, that we will arrange those files according to their sizes. So we will start with x4 with a size of 5, x3 with a size of 10, x1 with a size of 20, then x2 and x5 both are ranked 30. We will arrange it in the ascending order. Then, when we follow the optimal merge pattern, we don't have to find those different merge patterns, because now we know that by following the greedy approach, we'll be able to find the minimum. And the greedy approach is what? Take the pair among them which is minimum in nature. Minimum is 5 and 10, merge that. It will become 15. The next least pair, here if we see from this one, it is 20 and this is 15. Merge them, 35. Now look here what happens. Now this is 35 and 30 are remaining. So we need to take again least pair. So we it's not always that we should take this as 1 and this as 1. No. The two items which are remaining and which are lowest. Remaining are 30, 30 and 35. So the two which are lowest, we need to take that. So take 30 plus 30, it will become 60. Then the only items left behind are 35 and 60. Add them up, that will become 95. This way, calculating the total cost, either we need to add up 15 plus 35 plus 95 plus 60. That is those nodes, 15, 35, 95 and 60. These external nodes, we need to add them up, and whatever the result we get, That will be the total cost needed to perform this optimal merge. Either this way or another way is that we need to find the distance of every leaf node and some multiply it with the its value with the distance, that is di, and its value, and keep on adding that, which will get clear. Like if we take this leaf node as the first example, it's 5 5 into how much distance it is from this root node. So it is 1, 2, and 3. Multiply that 5 by 3 plus, since it is summation, go to second node, 10. So this is 10. How much far away it is? 1, 2, and 3. Multiply it with 3 plus, go to another one. It's 20. This is 20. And how much far away it is? Just 2. Multiply by 2. So in the same way, 30, 30, 30. This is 1 and 2, 1 and 2. Multiply by 2, multiply by 2. So this will again give the same result, 205. Okay. So now we will go to the Huffman coding. Is it clear till now? I am moving very slowly so that I will also understand what I am teaching. Okay, I will also understand my lecture. You are getting everything, I know. So Huffman coding is the 7th greedy technique. I have noted all those points here, starting from 1st to 7th. So this is the 7th greedy technique. As I said, this is a data compression technique. You are compressing, for so many applications we use the compression technique, and this optimal merge is having an application which has been utilized by this man for doing the data compression. Shall we start? So the thing is that if we are having a message like this, I had to transfer this message from source to destination, and the normal way which is being followed without the compression techniques is that we calculate the length of the message. Suppose it's 20 bits, 20 are there, the 20 characters are there from A to E, A, B, C, D, E. Yes, there are these 20 characters, and the ASCII value of every character, that is of 8 bit. For example, for A, its ASCII code will be like this. For B, it will be like this. So once we transfer this message from source to destination, neither the source nor the destination and nor the medium in between the two understands anything like this. The only language they are familiar with is this. So when we transfer such a message using the traditional components or techniques, the total size we need for this message will be the number of the elements in the message 20 and 8-bit ASCII code which we need for every character. So it will be needing 160 bits for us to transfer those 20 elements from one place to another. Now, can we do something better? Because as I can see that I am needing only 5 characters from the character set from A to E. So I need only 5 characters, and that also in uppercase. Okay, there is no lowercase involved, there is no numerical value, there is no special symbol. ASCII code gives us the 8-bit code, but for so many character set. Since in the present case, I don't have to deal with such a huge number of character set, I am having only 5 characters. So why not to develop my own code for transferring this data from source to destination with least amount of the bits needed? Why not to develop? Why not to bypass the ASCII code? Let me develop my own code, and the first one among the list is the fixed length code. The first one among those coding techniques is the fixed length. Now, coming to the logic of fixed length, here is the character set A, B, C, D, E. From A to E, my message contains those 5 characters. Let me count the number of times each character repeats itself. So if I say I have color coded here to make it differentiable from another characters. So this is A. So A is 3 times repeating. B, everything is red, 5 times. C, 6 times. D, 4, and similarly. So the total, if I add up, will be equal to 20, which is the actual message size. So I am having 5 characters. If I develop my own code for transferring those from station A to station B, in the binary language, how many bits I need? That will be equal to 2 power n. Because I need to code 5 characters. If I need to code 1 character, okay, if I am having 5 characters here, so the minimum number of the length of the code I need, that will be equal to 2 power n. If I take the value of n is equal to 2, means 2 power 2, so I could be able to code only 4 characters. But I need to code how many? 5. So if I take 2 power 2 minus 4, that will not work. If I take 2 power 4, that will be 16. But I need only 5. The remaining will get wasted. So I need to take minimum. So I will take 2 power 3. That's 8. Out of 8, I could be able to use 5 for coding. And if I start coding this character A, I will make its code as 000, 3-bit code. The code of B as 001, C as 010, D as 011, E as 100. So I had developed my own code. And this code is of fixed length size. Every code is of 3 bits. That's why it's the fixed length code. Yes. Now when I develop this code, so in place of this message I am transferring, I will now transfer their codes. I have written the message again here, B, C, everything here. So in place of B, this B, I will be transferring 001. In place of C, I'll be transferring 010. Similarly, the whole of the 20 characters will get transferred. And using this fixed length code, the size of this message will be equal to, it's 3 here, it's not 2, it's 3 into 60, 3 into 20, because we are having the 20 characters to be transferred. Yes, and for 1 character we need 3 bits. So 3 20 times, that will be equal to 60 bits. And in the previous case, when we used the ASCII code, we were needing 160 bits. But this is not only the case, because when we transfer or when we encode this message using this coding technique, our source should be somehow able to understand which technique we use for encoding. So at the source end, the destination should be able to decode back this 001 into original message. So we need to send those 60 bits as encoded message for this. In addition to it, we need to send this table also to the receiver. so that it will become comfortable for the receiver to decode it at the station B. So in addition to this, we need to send this table or the chat of codes, which we will be telling the receiver that which technique we followed to do the encoding at the destination side. So do the reverse of that to get the original message. So what we'll be sending to him is those 5 characters A, B, C, D, E. कि भाई A हमने इसके बराबर रखा, B हमने इसके बराबर रखा, C हमने इसके बराबर रखा, ऐसे कर करके. इसको 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 हटा दो, इसको कोई जरूरत नहीं है, ये बाद में है. इसको उसके साथ मत कंफ्यूजन कर दो. So 5 we need to send how many 5 characters, these 5 characters A, B, C, D, E. We need to send those 5 characters and we need to send them using their ASCII codes. Okay, because if we send them like this won't mean anything. We need to send him the ASCII codes of these 5 characters A, B, C, D, E. So we will send him 5 into 8 because 8 bits for one character. For 5 it will be 8 into 5, that is 14 bits. And in addition to it, we will need to also send him this code that A we have written like this, B we have written like this, C we have written like this, D we have written like this, E. Okay, so we need to also send him the code of how many bits, how many characters, 5, and how many bits needed for one character, it's 3. So 5 into 3, 15 for code. So that when this whole message, this plus this table reaches to the destination, he should be able to decode or get back the original message. So in total, we do the comparison by how many bits, 60 bits we need to send for the message as a whole. These 40 bits we need to send for A, B, C, D, E. That's which character set from the vast character set we used, and 15 for the coding purpose. So total of 115 bits we need for doing such type of coding if we use the concept of fixed length code. Okay, and initially we were needing 160 bits and there is about 150, about 35 to 40% reduction in the now there is another technique for compression that's even a modification or an improvement to this fixed length code, and that is the variable length. And variable length is the actually proposed by the Huffman. This variable length is known as the Huffman coding. And among the compression techniques, it is this variable length compression technique which uses the concept of optimal merge pattern. Okay, so that will be now discussed in the tomorrow's lecture.